Okay, this video is going to be a run through of everything that we did in board work today. If you weren't paying attention or if you missed it, if you were out today, I'm going to run through how to do all of the questions so that you're prepared for the quiz tomorrow. Sorry it's so late, but I do have to get home from school also to put this stuff up. But I'm starting with this slide from way back in the beginning of the year when I described to you what should be in your notes. And I'm now highlighting this section of the slide on application. When I say you don't have application in your slide, in your notes, what I mean is you didn't figure out how to do things that were explained in the slideshow, right? So if this was a math problem, what are the steps to doing that math problem? And even though a lot of times I will even give you steps, the only way you're going to learn how to do it is if you sit, figure it out, and write the steps out for yourself in a way that makes sense to you. So if I don't see you saying to yourself, okay, I'm going to draw a Lewis structure, here are the steps for that, then I think that you don't have application in your slideshow. So application is more than just doing practice questions. It is also the process of you figuring out how to do stuff. How do you apply what you're in your understanding section so that you can actually do the thing? So let's take a look back at the actual slideshow really quick. I did add some extra slides here. Uh, Shout out to Marissa Canale, who said I really needed this divided up a little bit better. So I added some extra slides. So there's now a title slide in between each section so that you can see what is each section about. Right. So I did gradually walk you through it, but I think it was hard for you to follow. What was I doing first? What was I doing second? What was I doing third? So the first thing I started with was I said to myself, if you're going to draw a Lewis structure eventually for something that's bonded, you're first going to have to know how do you draw a Lewis structure for just one atom. Okay. And so I go through a bunch of extra slides to make you review in case you don't know what a valence electron is. Valence electrons are electrons in the outermost shell. These are electrons that are used for bonding only, and that's why they are the only electrons that are drawn in a Lewis structure. Lewis structures are designed just to predict how bonding will happen. Um, and they are actually named after a person, Jan Lewis, right? So there's two ways that you can do this. One shortcut, it only works for the main group elements, that is group 1 and 2, and everybody, not the transition metals. Transition metals in the middle of the table are not main group elements. Okay, so you could use the group number. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. That's why these are all circled, right? You're in group 16. Oxygen and sulfur both have 6 valence electrons. And we talked again about the other way that you could do it is if you're on this periodic table that we're still using in the future, my kids are not going to get this periodic table anymore, is that you can look at the electron configuration. Now, some of you have gone online and gotten explanations about electron configuration that are too advanced for this class. And so you might be looking at something that says like 1s2, 2s2. That electron configuration is expanded out so that you can see where electrons are in very specific areas. This is organized only by energy level, right? So you want the electrons in the outermost shell, which is the highest energy level, right? The furthest away from the nucleus. So that would be the last number. But you'll see if you go down a group, right? 6, 6, it matches up with that group number. So whichever one works best for you. If they ask you about a transition metal, which on the old regions they do occasionally, you can read it directly off a transition metal on the table also. All right, so here are steps. This is me showing you the steps, but you have to decide that this is the step you're doing first. One of the things I noticed while we were doing board work is that you guys are trying to go straight to the answer without doing any steps. And so you can't figure out what direction to go in, and you don't know where you're making mistakes because you have no process that you've laid out for yourself. So step 1, write the symbol for the element. Step 2, you're going to draw dots for each electron. You are going to write only one at a time. Okay, this is really important. If you're going to use what you're drawing to figure out bonding, you can only draw electrons one at a time, because if you start pairing them off, it will look like those electrons can't bond, right? So we did this in class. This animation shows you how you put each electron in one place. So I'm going to quick go on the annotate and show you what I mean again that I talked about in lecture. And that is, if I were to do this like this, which I saw people doing in class, this one is technically correct, but we don't use it because this makes it look like carbon can only make 2 bonds. That's not true. Carbon can make 4 bonds. So if you draw it like this drawing will help you more figure out how to actually put these atoms together when you're making something. Okay, and another thing that you could do that this is the reason why this is correct is because there are some rules to how we do this. So this is, I would call this technically correct, but is it very useful for you to actually work with? No, I would call this a working model. In other words, this is more effective in helping you to draw these correctly. Okay, this is completely wrong. There's no reason for you to draw it like that. Okay, so one of the things that a lot of you had trouble with is trying to figure out why an atom is bonding, where it's bonding. And that is wherever there is a free space. If an atom does not have electrons paired off, they need an electron there. So remember what the goal is. Actually, let me pull my annotators. So Madison very cutely, Geraldo today called it the octopus rule. So the octet rule is one of our guiding principles, right? And like an octopus, it has 8, right? You want 8 electrons in this outermost shell. So if carbon right now is only showing 4, he needs to make 4 bonds so that he can get a second electron in each of these spots. Now, carbon in particular is probably not going to do this by ionic bonding, but it will do it by sharing electrons with other people. So I drew X's for all the electrons he might want to borrow from somebody else, and this now gives him his octet. So if you were to count with me, 2, 4, 6, 8, that's living the dream for carbon, right? If you're an atom, you want those 8 outermost electrons, and so this is your target goal. Mission completed if you can pull this off. So hopefully that explains it a little bit more, and we can move through. All right, so the first thing I do is I show you how to draw all your atoms out individually. You must do this first. You must do this first because you have to evaluate how many bonds each atom can make and where those bonds are going to go. Filling in the electrons one at a time also will help you with predicting the shape that the overall molecule will make if it's a covalent structure. Right? So when you're drawing water, your hydrogens are actually going to go in this spot. Right? You can see from each one of these atoms how many bonds they can make. Chlorine can make 1. Oxygen can make 2. Right. Then we're going to talk about why ionic and covalent are different. Okay. Fundamentally, the very first step you are going to do before you start drawing a Lewis structure for a chemical compound is that you have to classify it first. You have to know, is it ionic or is it a covalent? Because we show it in different ways because the bonding is actually different, right? I'm going to repeat that because I've said it in class multiple times, but I know that you're just not listening. Ionic bonding is different from covalent bonding. They are 2 different processes. And so we do not draw ionic compounds the same way that we draw covalent compounds. Okay? Since ionic compounds involve electron transfer, we do not show those atoms connected with lines because they are not sharing with each other. In a covalent structure, the atoms are bonding by passing electrons back and forth. They're actually sharing them, like I would share a pencil with my friend, right? So they actually can be drawn in diagrams that have lines connecting atoms showing that they're sharing those two electrons. Okay, every bond represents two electrons if it's covalent. If it's covalent. Okay, so the first thing we're going to talk about now is ionics. Ionics must be drawn in brackets. People who have to have their charges shown. If you gained electrons, you get to show your whole octet that you got. That made you happy. And usually the person who is in the front is the metal. They lost all their valence electrons. So since Lewis structures show only valence electrons, if you lost all your valence electrons to the other person, or you very generously gave them to the other person, you're not going to have any electrons shown in these diagrams. Right? So I'm going to leave you to go back over that because I want to hurry up and get to the quiz review. This section's on covalent. You must determine first if a compound is molecular or ionic before you start drawing. Okay, if you're doing a molecular compound, if you realize that the bonding is covalent, you've got all nonmetals. We're talking water, carbon dioxide, two oxygen atoms hanging out together. Those molecules are drawn this way. They are not drawn in brackets. So if I were one of those people who got a note in my notebook that said I need to do advanced understanding or advanced application, I would be pulling all this information together on one page in my notebook, trying to make sure I understand why do I do this here and why do I do that there, right? Make yourself like a table and try and get all this information all organized so that you understand where do some things apply and where do they not apply. The only reason I know it all is because I have it all categorized in my head, but I myself had to sit down and be like, okay, wait, this goes here, this can do this, but it can't do this, right? Like you have to sit and really study that or you're not going to get it. All right, now this section actually does have steps. So I would have expected to see some version of steps written in your application section to make sure you know how to do this. And I do show you the steps, right? Step 1, draw the Lewis diagram for each atom. Step 2, check out what's happening. Look at the actual Lewis structure and try and figure out how many bonds can that atom make and where are those bonding sites. Step 3, make sure you don't go past the limit, right? Each person has a limit to how many bonds they can make, and mostly that limit is really due to how many electrons they can take or share with other people. An atom is only so big, so they can only do so much bonding. And then the next thing is that usually when you're drawing a structure, the person who's first in the formula goes in the middle. Remember, this is only for molecules, not ionic structures. Okay, so here's what I did. First, I followed my own steps. First, I drew the atoms, right? So if I look at the first compound, ammonia, I first, on the left-hand side of the screen, I drew all the atoms. Then I looked, let me annotate so you can see, right? I looked at these individual electrons and I was like, okay, that means nitrogen can make 3 bonds. And these electrons that are not paired off, that's where you can make a bond. Where I have electrons that are already paired, you can't make a bond there. Okay, so I should not see people trying to link atoms in these locations. That's a no-no. Okay, only where you have a single electron can you bond. Now, hydrogen has nothing but single electrons. He's too small to have anything else. So he can use this electron to complete that bond, right? So they're going to share those 2 electrons between them. Those are shared electrons. This is what's known as a pair, 2 electrons, like a pair of shoes, an unshared pair, because it's not being shared between 2 atoms. Right? Hopefully that makes sense. And I'm going to get out of here because I think I've already taken too long doing review, and I want to run through the answers to the questions for the quiz review. So let me get out of annotating. All right, in-class quiz review. I'm going to do this relatively quickly because I don't want to make the video too long, because you also should have been paying attention during class. And I will have very little sympathy for you if you did not. And also because we have a lot of structures to do and I want to take some time to explain all that. So in the beginning, we talked about what is the difference between a fluoride atom, a fluorine atom, a fluoride ion, and a fluorine molecule, which is a diatomic molecule. Okay, I'm actually going to work backwards here. I think when you're looking at advanced understanding, the very first thing is, do you understand the difference between these three terms? Right? A lot of people froze on this question in both classes, and I think it's because essentially you really don't know your vocabulary. You're copying it all down in your notebook, but you're not understanding it. So I would sit there and compare these things, right? What is the difference between an atom, an ion, and a molecule? Okay? A molecule is a group of atoms that are sharing electrons, covalent bonding, right? So when you have a fluorine molecule, you've got two fluorine atoms bonded to each other. This is diatomic, so that's F2, right? Diatomic gases. And how are they bonded? They're both equally matched nonmetals, so they're going to share their two electrons to make sure that they both have enough. So to draw that as a dot diagram, you know what? I am being very bad right now. I am not drawing these the way that I just showed you to draw them. So people who get very fluent in this have a tendency to have these memorized, which is the only reason why I'm drawing my atoms all paired off already. If I did not have this memorized, if I was still on training wheels, which you are, I would do this like this. 1, 2, 3, 4, 5, 6, 7. I would draw two fluorines. 1, 2, 3, 4, 5, 6, 7. And then I would take a look at the bonding sites and I would say, okay, well, this electron's all by itself and this electron's all by itself. So that would mean that each of them can make a single bond. So if they bond with each other, that solves the problem and that makes them more stable. All these other electrons that are all paired off, they stay, but you're allowed to, in your picture, you're allowed to just move them to the other side so that it makes sense, right? So that's why I'm going to do that. I'll move this line. Let me redo that. I'm going to move those single electrons, this one and this one, into the middle, and then I'm going to put their other electrons back, right? If they're already paired off, they are not going to get shared with anybody. So that's what's creating that bond in the middle. Okay, a fluoride ion. An ion is a charged particle. So this is fluorine when it has picked up a -1 charge. You must, in a Lewis structure of an ion, show all of their electrons. Again, I'm cheating and doing them paired already. Fluorine, when it picks up that -1 charge, has picked up an extra electron. So that is where that all 8 electrons are coming from. But a regular old fluorine atom should not have 8. He only has 7 because he hasn't made any bonds yet to fix his little octet problem. Okay. What things are substances in chemistry? I'm just constantly reminding you that when you get to the regents, that word substance, which in everyday language sounds like it could be anything, is not anything. Okay, there's only 2 things that can be substances in chemistry: elements and compounds. And this is a pet peeve I have because I don't think we would say this in many other places in chemistry. I tend to find that the Regents does things in ways that are designed to just trick you. So you would typically say pure substance just to make sure you were clear that you were talking about elements or compounds, they dropped the pure. So now they're using the word substance like in the very everyday language way. And I think that's very rude and tricky of them. All right, what are the two types of bonding? That is ionic bonding and covalent bonding. In ionic bonding, electrons are transferred typically from a metal to a nonmetal. And in covalent bonding, electrons are being shared typically between two nonmetals. Okay, so this is where your old knowledge about bonding really has to, you have to pull that stuff out of your memory. I think we talked about this right from the beginning, right? Like this stuff does not go away. That was the stuff we've been doing since quarter two. That is the foundation of chemistry. So if you don't know it, you're really going to be lost. This, I think I pulled, number 4, I think I pulled that off of a Regents question. Is it particle arrangement or chemical reactivity that causes a substance's phase or state? After that, I clarified the question to jog your memory, but I'm pretty sure that this came off of a Regents and they would not clarify it for you. They would leave it at that. So here's some more vocab that if you don't know it, you have a problem. Phase and state are the same thing. Remember, that means that what I'm asking you about is, so one trick you can use if you do know what this means is you can take what you know and put it in the sentence while you're reading it, and that will help you make sure you understand what they're asking for. So, is it particle arrangement or chemical reactivity that causes a substance to be a solid, a liquid, or a gas? Right? Solid, liquid, gas is a physical thing. Freezing water or boiling water does not require a chemical reaction. And that's why this is a physical physical thing is based on particle arrangement, not chemical reactivity. I hope that's clear. Make sure that you're doing that for yourself. That's a very good reading strategy to help you, especially to decode these ridiculous Regents questions. Almost done, except drawing structures is going to take some time. So how does an atom of nitrogen acquire a -3 charge? Please make sure you don't have this backwards. This subtraction does not mean you are losing. This plus does not mean you are gaining. What you are actually doing is counting negative charges or counting positive charges. If you still don't understand this, please go back to the slideshows and review. I went over it like multiple times. I still have people telling me, oh, this is so repetitive, so I didn't take notes on it another time. And then I watch you right in front of me, you don't understand the material. So that means that there's a reason why it was repeated, because I already knew that you weren't going to understand it because I've been doing this for 20 years. So if I put it back in there again, it's because I know that on some level you don't know it. If you really and truly know it, make sure you prove it to yourself before you skip it, right? Nitrogen gains, it gains 3 electrons to get that charge, and calcium loses 2 electrons to get that charge. So that's the correct answer. All right, we've got a lot of Lewis structures to do. And if you didn't get it all written down in class, I'm going to rattle them off really quick. I'm going to steal these and throw them into a paint slide so we could do it together. Yeah, that's a big old list. Okay, I'm going to be doing this very quickly. So remember, you can rewind me or you can pause me. First thing I'm going to do is I'm going to go through and find who's ionic and who is covalent. So covalent people are going to be drawn with line structures in my version of this. And ionic people are going to be drawn in brackets, which is the only way you can draw them. There's actually a lot of covalence here. There are a couple of ionics, though. Calcium oxide, potassium bromide, and potassium iodide. Since that's the shorter list, why don't we draw the ionics first? Remember that you are new at this. So go ahead and make sure that you draw your Lewis structures first, right? If I draw these two Lewis structures for just the atoms, I realize, and I'm going to use color coding here, what I realize is that this oxygen needs another electron here and another one here. This calcium just coincidentally has two electrons it could give oxygen, and he could put those electrons there and the electrons there, and then that will have octopus, an octet, and he'll be happy, right? So that's what they're going to do. This is what it means in an ionic bond for this to be a transfer. Calcium will transfer its electrons to oxygen. In the process, calcium will pick up a +2 charge. Oxygen will now have all 8 of the electrons it wanted. So I'm going to show all 8. And then give him a -2 charge, because that's what you get if you get 2 extra negative charges, 1 for each of those electrons. Okay, so I'm going to, hopefully that was a quick enough explanation. I'm going to jump ahead and go ahead and do that again for potassium. I'm doing this wrong. Charges have to go outside the brackets. I don't know why. They made up, these are rules. They're conventions that everybody has to follow so that we're all drawing the same diagram. But it's a little bit weird. Okay, and then potassium iodide is exactly the same as this one. So same thing, I want you to draw your atoms first and make sure you understand what happened with this electron transfer. All right, that's all of ionics. Not that hard. Let's do the covalents. They're a little more involved. Oh, actually, you know what? I'm in paint. I don't need to do that. All right, so those are my ionics. Let's start with water. You go with a bigger line thickness because we got to draw a lot of dots. All right, everyone knows water, right? H2O. Right? I do need to take a look. Hydrogen looks like this, 2 of them. This says 2 of them. Oxygen, 1, 2, 3, 4, 5, 6. Hey, I did see a whole bunch of people draw oxygen straight across like this. Sorry, water straight across like this. This, people will take this as a Lewis structure. It is technically not ideal, because if you do it with this method, right, where I look at hydrogen and I say, okay, this hydrogen will go here and this hydrogen will go here, I will actually get a structure that shows me that water actually looks like this. And it is a bent molecule, and that contributes to understanding if its shape is symmetrical or not, which comes in later when we do intermolecular forces. And so those of you who know what I'm talking about when I say polarity of molecules, it helps you predict if the molecule is polar. So if you're drawing these shapes wrong, it will actually cause problems for you later. Okay, so these are 2 different versions of this. Both of them are correct. All right, I'm going to rattle through the rest. I have a feeling I went way, way over time. All right, let's do carbon tetrahydride. Carbon, 1, 2, 3, 4. Each hydrogen will have 1. You can see that carbon, if he wants 8, he's going to need to put a hydrogen in each one of these spots. So he's going to do this. Right? If this is why I sometimes draw them as X's, especially if I can't color code, right? If hydrogen's electron is an X, what I can do is show how this is sharing, right? One of these belongs to carbon, one of these belongs to hydrogen. So here's carbon's original electrons, and then he gets the hydrogens to come over and share theirs with him. And then this gives him 8. Right? Remember, hydrogen is happy to not have 8. He's too little to hold on to 8, so he'll just use 2. 2 makes him happy. right? So that's what it looks like. All right, let's do somebody who's got multiple bonds because those usually confuse people. I personally did not learn how to draw Lewis structures this way. When I first saw this, I was like, this is stupid. I learned to do it with this long list of rules where you like calculate out all the valence electrons and figure out where to put them based off all these rules, like a big long list of rules. I think that this is better in some ways. This picture method, it's quicker for me to teach it to you. And it does predict the structures better than if you're using the rules. But what this kind of is weak on. So there's three people here that have double and triple bonds, diatomic oxygen, diatomic nitrogen, and carbon dioxide. So you're going to find that when you're drawing these as pictures, you may find that it's a little harder to see it as a picture as opposed to the way I learned it, right? So I'll start with carbon dioxide. So I draw my carbon and my oxygens, right? Dioxide, two oxygens, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? So things have not changed. Carbon still needs to make 4 bonds so that he can have 8 electrons. And oxygen, each of these still need to make 2 bonds so that they can get all of their electrons taken care of, right? He's only got 6, so he actually needs to have 2 of these sites filled to get 8 around him. So the rules say if I put the one that comes first in the middle, what I'm going to do is put the other atoms around him. Okay, and then I'm going to try and get all their electrons to line up. So when I draw my oxygens, oh, problem with all these dots, man, is they go every time I touch the screen. 1, 2, 3, 4, 6. All right, and now what I'm going to do is because I want my single electrons, the ones that can actually bond with each other, I kind of want them facing each other so that in the picture it's a little easier to see. So I'm just going to go ahead and put my pairs on the other side. So it's a little easier to see actually, do that, where these guys are going to go. So I've got 2 here that can bond. I've got 2 here that can bond. And so what's starting to become clear, what I basically want to do is move those single unmarried electrons in between these 2 nice people so that they can bond, right? So I'm going to go ahead now and I'll draw it as a dot structure. Then I go ahead and put these pairs that can't bond because they're already paired, I put them back. Right? And then I'll do it again here. Now, if you want, you can draw each of these pairs that are making a bond, you can draw that as a line, which will look like this. And then we usually put the unshared pairs like that. Okay, and that's carbon dioxide. So it's not hard to do the ones that have double and triple bonds. It's just if you don't do all the steps, like draw all your atoms out and then evaluate where everything is, you're not going to be able to make sense of it. And you're probably going to get it wrong. Okay, most of you are just not giving yourself a chance to really process it. So I'm going to very quickly give you the answers to diatomic oxygen and diatomic nitrogen. See if you can go back and do what I did and figure out why it looks like that. So oxygen will look like this, and nitrogen will look like this. You'll sometimes see people put the pairs here. That's fine too. But typically we leave them on the top. All right, so break it all down and see if you can understand how I did that. All right, hopefully this probably went too long. Sorry, you guys, but hopefully it helps if people see it.